All this kind of stuff is possible because of miniaturization. Okay? Now you can make this circuit small enough and put it in there. Okay? You guys might have seen good quality amplifiers back in the day, and they were in big boxes and stuff like that. Right? And now you see that big box can be squeezed into this little thing. Of course, this little thing won't do as good a job as the big box. The big box maintains the quality of the waveform. Anyway, that's what that is. Okay. So, before I get into this, this chapter is about the following. Okay. And this chapter will turn into a whole course called circuits when you get to your junior or senior level. Okay. And this is what this thing is about. Okay. Again, the power delivered to a device is V times I, or we'll say I square R. This is the power delivered to this device. That's the current flowing through that device. Okay. And the power delivered to a device tells you how bright it glows. Or if it's a toaster, you know how fast your toaster will happen. If it's a washing machine, if it's a dryer, how fast your clothes will dry, and so on. If it's a bulb, it tells you how bright the bulb will glow. So you really want to know the current through all devices, so to speak. That tells you how bright it glows. Okay. So here's a circuit. In this circuit, so there are multiple sources, and there are multiple branches, and so on. Okay, multiple loops. So what we want is, if you have a complicated circuit like this, and you saw an example earlier. Okay, so here's the circuit. What you want to know is what is the current passing through each device. Okay, you want to know what is the current passing through each branch. Okay, and that's what we mean by solving a circuit. Okay, so in this thing, this is a branch, that is a branch, and the current flowing through all parts of one branch is the same. Okay, what we want to know is the current flowing through each element. And that's what solving a circuit means. And why do you want to know how much current is flowing through each element? Why do you want to know how much current is flowing through each element?
Because it tells me how bright.
Exactly, that how bright it's glowing, okay? How fast it's cooking your pizza. And these two rules allow you to solve circuits. So an entire course is based on these two equations. And these are Kirchhoff's rules. Okay, so let's try and understand these rules. And they're very simple. Okay, what this rule is telling you is, this is the current rule. It tells you the current flowing into a junction is equal to the current flowing out of a junction. And what is a junction? This is a junction. A junction is where more than two arms meet. So here's one arm, here's another arm, here's another arm. Okay, so that is a junction, and this is a junction. Okay. So what this current rule is telling you is the amount of current flowing into the junction is equal to the current flowing out of the junction. And that makes sense, because if the amount of current outflow is not equal to inflow, then you'll have charges collecting in that junction, and that doesn't happen in a circuit. Okay. All right, so according to this rule, okay, this current is flowing into this junction, this current is flowing into that junction, and this is the current flowing out of the junction. So what this rule tells you is I1 plus I2 should equal I3. Okay. All right, what is it that we started with? We wanted to solve the current in all the elements. Okay, so what we did was we said the current in this branch was I1, the current in this branch was I2, and the current in this branch was I3. I1, I2, and I3 are like X, Y, and Z. They are the unknowns, and we're trying to solve for those unknowns. Okay, so for this circuit, how many unknowns are there? 3. I1, I2, and I3. How many equations do you need to solve 3 unknowns? 3. Okay, so this current rule gave you this one equation. Yep. You need 2 more equations. Okay, and now this is the voltage rule. The voltage rule tells you the following. Okay, before I tell you the voltage rule, let me do a physical analogy. Let's say this is a mountain, and you go for a hike in this mountain. Okay, let's say you start off there, and you go for a hike, and you come back to your starting point. What is your total elevation change? 0. Okay, that's what the voltage rule says. Okay, so the voltage rule says, at every point in a circuit there's every point is at a certain voltage, and if you go around a loop and come back to the same point, what is the total voltage change? 0. And that's what that is rule. The voltage rule says. The sum of the voltage changes across all elements adds up to 0 when you around a closed loop. That's what this voltage rule says. Okay, so let's say you start here, and let's say the voltage change across this resistor is plus 5 volts, the one across this is minus 4 volts, and so on, and you add up all the voltage changes, come back to the starting point, they will all add up to 0. Okay. So those 2 simple rules are Kirchhoff's rules, and they will help you solve circuit problems. Okay. So we'll apply this to DC circuits right now. We'll apply this to AC circuits in another chapter. But these 2 equations will be the basis for an entire course, the circuits course. Okay. All right, so let me apply this rule. Okay. How many loops does the circuit have? 1, 2, 3. Okay. Okay, so you will find that a circuit will have many, many loops. Okay, so for instance, okay, let's see if we have another example. All right, we don't have another example. This circuit has, you will get a headache trying to count all the number of loops. 1, 2, 3, 4, 5. I mean, it's got an infinite number of loops. Okay. All right, so let's do that. Okay, now, so let's use this rule to get a couple more equations. Remember, we want 2 more equations. Okay. Now here's the rule. Which direction? So you chose the direction of the current like that. Okay, and that's an arbitrary choice, and it won't affect your answers. Okay. Currents flow from a higher voltage to lower voltage. That's what you want to remember. Okay, currents flow downhill. So when you go with the direction of the current, the change in voltage across this element, okay, so we'll go around, we'll call this loop L1, we'll call it loop 1. Okay, so currents flow downhill. So when you go across this element, the voltage decreases. So that is I2 R2. The change in voltage across that element is that, okay? Minus I2 R2. And then again, you're going from a high voltage to a low voltage. And this tells you this is the EMF of the battery. And that tells you what is the voltage change when you go across the battery. Minus E2. Then what is this? What is the change in voltage across this element? Again, you're going with the current, you're going from high voltage to low voltage. So it's minus I2R2. Okay. Then you're going across this element. What is the change in voltage? Minus I3R3. And you come back to your starting point. So the change in voltage should all add up to 0. Did you guys understand that? All right. Well, we will be solving problems. I'm just showing you how to set up equations. Okay. So again, well, what is the ultimate goal? The ultimate goal is to find these three currents, I1, I2, and I3. Those are the three unknowns. Those are the X, Y's, and Z's. Okay. And what we're doing is we're setting up equations to solve for those three currents. So here's the first equation. This current rule is the easiest one to use. And this is the voltage rule, okay, so that we're applying. Here's loop 2. Okay. So let's write down the equation for loop 2. All right. Again, for a given loop, you can start anywhere. Okay, so let's say you start here, and you can go in any direction, clockwise or counterclockwise. So for this loop, let's go like that. We'll go around the loop like this and come back like that. All right, here's the first element. Now you're going against the current, so you're going uphill. What is the equation? Change in voltage. When you're going uphill, the voltage increases, so it increases by I1, R1. Then the next element you're going through is, again, you're going against the current. The current is flowing like that. I1 plus little r1. And then you're going from high to low voltage, so it's minus E1. And then you're going against the current, plus I3R3. That should add up to 0. All right, so again, using the voltage rule, you can get many equations. And you start off by using the current rule because that's the easiest to use. And then you use the voltage rules to set up your equations. Now we have 3 equations, and we should be able to solve for these. Okay. So in a problem, they'll obviously give you the values of these resistors and the values of these voltages. And so I1, I2, and I3 will be the only unknowns that you'll be solving for. Okay. All right, so again, what are the 2 Kirchhoff's rules? The 2 Kirchhoff's rules are the current flowing into a junction. The current flowing into a junction is equal to the current flowing out of the junction. The sum of the voltages across all elements in a closed loop add up to 0. Okay. Those are the 2 rules. And like I said, these 2 equations are going to be the basis of circuits course. Okay. You'll just learn various elements. Okay. All right, so again, when we do examples, you'll understand those equations better. Okay. All right, so again, here's a circuit, a useful circuit, and like I said, you are interested in finding the currents through each element. This is a transistor, this is a capacitor, this is a diode, these are resistors, capacitor, and so on. Okay. So you can see there are 4 different kinds of elements: resistors, capacitors, transistors, and diodes in this circuit. All right, so we saw that here's a battery. EMF of a battery is the maximum voltage that the battery can provide. So the EMF is the maximum voltage the battery can provide. Okay. So when you buy the 1.5 volt battery, what that 1.5 volt means is the maximum voltage it can provide. Okay. Normally, as the internal resistance of the battery increases, the voltage it's providing is less and less. And you can think of a battery, when a battery is dead, that means its internal resistance, you can think of it as has gone to infinity. Okay, so that's a way of thinking about it. All right, so EMF is the maximum voltage it can provide. Okay, what is voltage? That's the potential energy per unit charge. Okay, so remember, voltage was potential energy per unit charge. Okay. Anyway, so what does a battery do? So what a battery does is this is the conventional direction of the current. That would be positive charges moving in this direction. But in reality, it's really electrons moving in the opposite direction. Anyway, okay? So here's what the battery does. Here's a positive charge. A positive charge has high potential energy here. And then as it goes through the device, when that potential energy goes through, for instance, a toaster, it's losing its potential energy. And what is it doing? Converting that to heat in a toaster. Okay? So that's what happened. Electrical energy got converted to some other form of energy in that device. Okay? So it's lost its potential energy, and then it's come back home to the negative terminal of the battery. And then what does the battery do? It converts some of its chemical energy and transfers that to potential energy, electrical potential energy. And now that charge can do its stuff again. Okay, it goes through the device, comes back, it's lost its energy through the device, comes back, and then again some of the chemical energy is converted back to electrical energy. Okay. And how long can you keep doing this? Yep, till you run out of chemical energy. Okay, so that's from an energy perspective. All right, so here's a battery. Here's the symbol for the internal resistance of the battery, little r. Okay, here's the load. Okay, so this is the outside of the battery. The EMF is the maximum voltage it can provide. The voltage you see, VB minus VA, VB minus VA, is the maximum voltage it can provide, minus I times R. See, when a current I is flowing, there's a voltage drop across this internal resistance, which is that, I times R. So what you're seeing is the maximum voltage minus this. When do you see the maximum voltage? When can you see the maximum voltage? When internal resistance is 0. Then you can see the maximum voltage. Okay. So this is called the terminal voltage, what you get to see. Okay. And the terminal voltage will be close to the maximum voltage, the EMF of the battery, if R is small. Okay. And the internal resistance, if it's small compared to the external load, the terminal voltage will be close to that. Okay. So for you to see, for the terminal voltage to equal EMF, this needs to be negligibly small, the internal resistance. Okay. So what this graph is showing you is voltage at A. There is the EMF inside the battery, and at the terminals you're seeing a slight voltage drop, and then when you go across the load, the voltage drops all the way. Okay, so there's a voltage drop across the load. Okay. So the current in the circuit is the EMF of the battery minus the internal resistance plus that, okay? The EMF of the battery divided by the total resistance in the battery, in the circuit, okay? What this is the power delivered by the battery is the EMF of the battery times the current drawn from the battery. That's the power delivered by the battery. And what this equation tells you is I square R, that is the power delivered to the load. That's the power delivered to your toaster. What is this fella? I square R. What is this little r?
The battery's internal.
That's the internal resistance. So that's the power dissipated inside the battery. That's the power wasted. Yeah, that's what makes your batteries warm. Okay. So that's wasted energy. Okay, so the power delivered by the battery is this much. Out of this much gets to the load, and this much is wasted in the internal resistance. Okay. So you see, if the internal resistance is comparable to the load, you're wasting a large amount of your energy. Okay. Okay, here are resistors in series. When you connect devices like that, these are resistors in series. And the equivalent resistance is just the sum of these guys. Okay, so the equivalent resistance is just the sum of those resistors in series. When you have resistors connected in series, the current flowing through them is the same. Okay. But the current is greater the resistance, the smaller the current. So when you connect a whole bunch of things in series, the current decreases. Here are resistors in parallel. Okay. So you connect it like this. Now, each resistor sees the same voltage. Okay. So when you connect the devices in parallel, if you connect this battery, if you connect just this guy, he'll get the same current. And if you connect something else in parallel, the amount of current does not decrease here. Okay. So let me draw that again. So here's the voltage. Here's R1, I1. And I connect the same voltage source. This I1 is the same as this I1. Okay, so when you connect devices in parallel, the current through each of these is the same as if it were connected by itself. Okay, so this parallel connection, okay, what did it do? If you connect two bulbs to this battery, now this bulb is drawing a current and this bulb is drawing a current. So you're running the battery down faster. Okay, but this is how your housing wire is connected. So there's the power source coming to your house, and each device in your house is connected in parallel. Okay, so whether this guy is connected or not, this guy will draw the same current. Okay, so every device in the house is connected in parallel. Every house in the neighborhood is connected in parallel to the power source. Okay. And with that way, whether you're operating or not, doesn't affect other person's operation or not. Okay. So That's a parallel connection. Okay, so if you have two resistors connected in parallel, the equivalent resistance is given by this formula. And what this formula tells you is this equivalent resistance is less than any of those guys. Okay, see, 1 over R1 is a positive number, that's a positive number. So it's a series of positive numbers. And so this guy has to be greater than any one of those guys. And so this guy has to be smaller than any one of those guys. Okay. Anyway, so the equivalent resistance is always smaller than the smallest resistor. All right, so coming back to this, if you want to make a bigger resistance, you want to connect them in series. If you want to make a smaller resistance, you want to connect them in parallel. Okay. So that's how you combine resistors. So here's an interesting problem. I've known this for a long time. Okay, well, so here's the problem. So let me simplify this. So let's say we connect an infinite ladder of 1 ohm resistors. Each is a 1 ohm resistor. What you want to find is what is the value of R. Okay, so I'll give you a hint. So let's see, if you connect resistors in parallel, what do? You decrease the value of the resistance. Okay. It's smaller than, and if you connect resistors in series, you're increasing the value of resistors. Okay, so let's come here. Okay, so imagine this was not there. Then this would have been 1 plus 1 plus 1, 3 ohms. Okay, but you connected this guy in parallel to this guy, so his value reduced from 1. So there was 2 ohms here, and this is effectively less than 1. So R has to be between less than 3. Okay. It's some value between 2 and 3. Okay. So if you solve it independently, I might give you $1. So that's a challenge problem. Okay. All right, so here are Kirchhoff's rules again. Okay. You will run across complicated circuits like this. Okay. You'll run across circuits that have multiple sources and multiple devices connected to it. And what you will want to do is find the current through each branch of the circuit. Here's a branch, here's a branch. Okay. And in a given branch, the current flowing is the same, okay, through all elements in the branch. Okay. So solving a circuit will mean finding the currents through each branch. Okay. And to be able to solve that circuit, these 2 rules help you do that. The current rule tells you that the current flowing into a junction is equal to the current flowing out of the junction. So the sum of the currents flowing into a junction is equal to the sum of the currents flowing out of a junction. Okay. What is a junction? Any point where more than 2 branches are meeting. Okay. That's a junction. So currents flowing into a junction is equal to currents flowing out of the junction. And it turns out that if you write the equation for this junction or this junction, you'll get the same equation. Okay? And the voltage rule tells you that the change in voltage across each element around a closed loop adds up to 0. Okay? And that's the voltage rule. So those two rules help you solve circuits. Okay? You guys understand that? And what does solving a circuit mean? Finding the current through every loop, and that tells you the current through every element in the circuit. And why do we want to know that?
That tells us the power output of each.
The power being delivered to each device. Okay, and that'll tell you if it will burn out or whatnot, or if it'll do its job. Okay, and so on. So if you want to make sure that the pizza cooks in 5 minutes, if you solve for the current through that oven, you'll know whether the pizza will cook in 5 minutes or not. Okay? All right. So here are the voltage rules. Okay, so when you're going with the current, current flows from, so you can think of current as water flowing. Water flows downhill. So the voltage change across this is minus IR. When you go in the direction of current travel, then the voltage change is minus IR. If you're going opposite to the direction of current flow, then you're going uphill, and change in voltage is plus IR. This is the negative terminal of a battery. So when you're going from negative to positive terminal, the change in voltage is plus V. And then when you're going from positive to negative terminal, the change in voltage is minus V. Okay? So you have to remember those two rules. Again, the easiest way to remember is think of this current as water flow. And when you're going with the flow, change in elevation is negative. When you're going against the flow, change in elevation is positive. Okay? The battery, when you're going from negative to positive terminal, the change in voltage is positive. And when you're going from positive to negative, change in voltage is negative. Okay. So again, to solve a circuit problem is to find the current through all the elements. Okay. To solve the number of equations one needs is equal to the number of unknown quantities. Okay. Which rule is the easiest to apply among the two? The current rule, the junction rule. Okay? That's the easiest to apply. And then once you've applied that, then you count how many more equations you need, and you find that many loops. Okay? And as you saw, topologically, you'll always be able to find enough loops. Okay? So in this chapter, we are applying those two rules to DC circuits. In another chapter, we'll apply the same rule to AC circuits. But just these two rules will make up a course. Okay? So here, we'll apply this rule to an RC circuit. What is an RC circuit?
Gas, resistor, capacitor.
It has a resistor and capacitor. That's what that is. All right? R is a resistor and C is a capacitor. Okay? You will be surprised that this circuit will be used in many, many places. Okay? So, where is it used? It's used in your flash camera. It's used as a heart defibrillator. It's used as a pacemaker. So very diverse applications. Okay. So here is the basic circuit. Okay, and this is in various forms. Okay, so here's the capacitor, here's the battery. Okay, what does a pacemaker do?
It like sends electricity to your heart at like a constant rate.
Yeah, why does it do that?
Because your heart rate is your heart is like out of sync. It's like out of the.
Right. So if your heart doesn't beat regularly, okay, so your heart. Okay, so your heart itself has an electrical system. It starts the beat by sending a pulse over there, and then the pulse propagates. Okay, so it's a sequence of compression. So first the right atrium compresses, and then the next left, right. So atrium and then the right ventricle sends the blood to the lungs. Blood comes back to the left atrium. That compresses, sends the blood to the left ventricle, and the left ventricle compresses, and the blood gets sent to the entire body. Okay, so there's a sequence of, the sequence of firing. And if this doesn't start beat every 70 times a minute or whatever, for if the electrical system is messed up, if you send an electrical pulse every 70 times a minute, you make the heart beat regularly. So you're assisting it. That's a pacemaker. So here's the circuit for that. Okay. So you close this circuit, you close the switch, the capacitor charges, and then when you want to make the heart beat, you close the switch, and the capacitor discharges through your heart, and you get the heartbeat started. You set the parameters such that this thing, you're closing the switch 70 times a minute. Okay? So you can make the heartbeat at a regular pace. This same circuit is used in your flash bulb camera. Close the circuit, charge the capacitor, and then when you want to take a picture, close this circuit. When the capacitor is charged, this opens. You open this. When you're ready to take a picture, close the circuit, and here's your flash bulb. This same circuit is the defibrillator. You close the switch, charge the capacitor, and when you want to jumpstart somebody's heart, you close the switch and pass that current through their chest cavity. Yep.
What's the purpose of the first resistor?
Oh, this tells you how fast you're charging the capacitor. Yep. So these resistors, we'll come to that in a second. These resistors control the rate of charging and discharging. Okay. You'll see that greater the resistance, slower it will charge. Smaller the resistance, the faster it will discharge. Yeah. So the time constant of the circuit, roughly the rate at which it charges and discharges, is RC. You see, the greater the resistance, the greater the time constant. So now that you understand that, okay, so here's the resistance, okay. In the circuit, you close the circuit and the capacitor discharges through your heart. So that's a pacemaker. And now if you have a pacemaker and if you want to go for a run, what do you need to do? You need to discharge more often. How do you discharge more often? You see, if you reduce the time constant, if you reduce the resistance, in the circuit, then you can discharge it more often. Okay, you have to charge it faster as well. So you have to have some sort of way to monitor if you're going for a run, your breathing rate increases or whatever. And then you put in a circuit so that you reduce the resistance in that circuit. So now there are smart pacemakers. Okay. So you can do that. All right. So this is a very versatile circuit. Okay, it's used in many places. Okay, so let's look at this RC circuit. Okay, so what we're going to do is first we're going to look at just this half of the circuit. Okay, we're going to study just charging part of the circuit. Okay, what is the charging part of the circuit? And what did you do in the charging part of the circuit?
You put charge on the.
You transferred energy from here to there. Why did you do that?
So that you could release it all at once.
What's that?
So that you could release it all.
Very good. Because this device, you never want to forget the fundamentals. This device can release the energy much faster than this device. Okay, so that was why you had this part of the circuit. So the first part of the circuit moved energy from here to there. And from this device, you can release it fast, energy fast. Okay, so let's just look at this part of the circuit, which is what this is. Okay, so here's the capacitor, here's the resistor, and here's the switch. Okay, and there's the battery. Okay, so let me show you a little. Okay, let me show you the little app. No, I'll show it to you after the math. Okay, so let's do the math first. Okay, so we've closed the switch. What is this? A closed loop. What does Mr. Kirchhoff have to say about that? He says sum of the voltages across all elements in the circuit must add up to 0. And that's where that equation came from. Okay? So what we'll do is we'll start here. We'll go across this loop like this. This is plus E. And this is the charge. We're wanting to learn how the charge in the capacitor builds up. Okay, so that is QT. So this is Q as a function of time. Okay, minus. Okay, so this is charge positive. So this is at a higher voltage than that. So when you go across this, that is minus QT over C. Remember, the voltage, charge, and capacitance are related like that. Okay, as the charge builds up, the voltage across the capacitor is increasing. Okay, so minus QT over C, and then as the capacitor is charging, the current is flowing like this, and so it's minus I times R. Okay, so that equation is minus QT over C minus IT, current as a function of time. Okay, so as the charge builds up on the capacitor, the voltage increases, this term increases, and the current decreases. Okay, so as this gets smaller and smaller, this gets smaller and smaller. This doesn't. Okay, as the capacitor charges, this current dies, and this current will go to 0 once the voltage across the capacitor is equal to the voltage across the battery. Okay, so if the battery is a 10-volt battery, once the voltage on the capacitor builds up to 10 volts, then the current goes to 0. Okay, so once the voltage across the capacitor is equal to the voltage of the battery, then the capacitor is fully charged. All right, so we want to know how the charge builds up. We want to know what is QT as a function of time. Okay. All right, well, how are Q and I related? I, the current in the circuit, is equal to dQ by dt, the rate at which the charge is building up. So this is really a differential equation. So this is really E minus 1 over C QT minus R times dQ by dt. Yep. So this is one of the reasons why you study differential equations. What is this telling you? This is your system that you're studying. This system is changing with time. The dynamical behavior of this system is described by this differential equation. Here is a mathematical model for the behavior of this system. Okay, what do you gain by, what will happen when you learn to solve this equation? You'll get Q as a function of time. You'll know how the charge on this capacitor builds up. Okay. All right, so again, you learn various techniques to solve these differential equations. Okay, so with the simplest equation, you guess at the answer, and then you learn to various techniques and learn to guess better and better. Okay, here is the solution. Okay, you can plug this back in here in this equation and verify that it is indeed a solution to that differential equation. Okay. So here's how the charge on the capacitor builds up. Okay, it builds up exponentially. So there is the maximum charge, C times E, 1 minus e to the power of minus t over RC. There is the time constant in the circuit. Okay, so that is the time constant is given a special symbol tau. Okay, and that tells you that's the time scale over which all things change. Things change in that circuit. Okay. So if you make the time constants greater, the capacitor charges slower. Okay, so here is a time constant of 2 seconds. Here is a time constant of 0.5 seconds. Okay. So that's a capacitor that's charging faster. Okay. And you see this is the current. Current is dq by dt, and as the charge builds up, the current in the circuit is dying. Okay. As the charge on the capacitor builds up, the voltage builds up, the current is dying. Okay, so what happens is the following. When you first close the switch, electric field is established in the wire, which drives the current. And as the charge builds up, this electric field goes to zero, and that current goes to zero. Okay. All right, so now I'll show you this in an app, and it'll happen so fast you won't be able to see all the details. Well, but anyway. Okay, so I guess we're increasing the voltage, and you see what happened was current flowed from here, electrons flowed from here to here. These repel the electrons, and it discharged. Now once this thing is charged, you've stored energy in the capacitor, and you can discharge this energy anytime you want. What can you do with this energy stored in the capacitor? Discharge it through a flash bulb. You can discharge it through the thoracic cavity of a person to restart their heart, or this could be energy stored in a pacemaker that can be used to start a heartbeat. Okay. So once you've got energy stored like this, okay, in a capacitor, then you can use it any way you want. This could be a capacitor in a supercar, and you stopped at a red light and discharge it through your motor and take off faster than anybody else can. All right. All right, so a capacitor charges exponentially. The charge builds up exponentially, okay, and the current dies exponentially. All right, now now we'll look at the second part of the circuit. Okay, so once we've looked at this part of the circuit, we looked at charging the capacitor, and now we'll look at discharging the capacitor. Okay, So you're discharging the capacitor through, remember this circuit was also used in a fusion reactor where this would be a laser shooting at a pellet. Okay. All right, so now we'll discharge the capacitor. Okay, again, once we close this, again, all these changes, by the way, are happening very, very fast. Okay, so charging is happening over a second or two. See, charging is happening over a second or two. And most of the time, the discharging is happening over milliseconds. Okay, so we're studying phenomena that are happening very fast in the blink of an eye. Okay, so we charge the capacitor, and now we'll close this circuit and discharge it. Yep. All right, so we want to see how the capacitor discharges. Again, this is a closed loop, and so we can set up, using Kirchhoff's voltage rule, we can set up an equation. Okay, so we'll go, so let's go across like this. Okay, so that's what this circuit is. So when you go from here to there, you're going from high to low voltage, so it's minus QTC. And then you're going against the current, so it's plus IR equal to 0. But now you got to be careful. See, as the capacitor is discharging, what is happening to Q? The charge is decreasing. So the current is minus dq by dt, because this is decreasing, this will be negative, and negative will give you positive. Okay, so the current is that. Okay, so there is your differential equation. R times dq by dt plus q over c equal to 0. Okay, so here is the differential equation modeling the behavior of this system. Okay, and you can solve this differential equation. Okay, so here's a mathematical model for the behavior of this system. Okay, and that's what you'll do as engineers. You'll have a system and you'll come up with a model, and you'll study this model and verify, make sure that your model will be good if it predicts the behavior of the real system accurately. Okay. All right, so the solution to this differential equation is that. So QT is, okay, that's the maximum initial charge, and the charge decreases exponentially, again with the same time constant. Okay. And you take the time derivative of that, that'll give you the current through the circuit, and that's again decreasing exponentially. Okay. All right, so that was quite an analysis for this little simple circuit. Okay. But again, once you learn this piece, then this, you can add more and more complications. So we learned how to charge and discharge a capacitor. Okay. And now we'll use that in applications. Okay. So a pacemaker, this is a dual chamber pacemaker. Anyway, a pacemaker, if your electrical system, the heart's electrical system is malfunctioning, meaning it's not beating regularly, then you install a pacemaker. Okay, and again, here's the basic pacemaker circuit. Effectively something like this. What you do is you charge this capacitor, and on a regular interval or as and when needed, you discharge the capacitor through, not through your heart, but you send a signal to the appropriate starting point to get the heart beating. Yeah. So a normal heartbeat beats at regular intervals. The heart's own electrical signal regulates its beating. If for some reason the heart does not beat regularly, a pacemaker can be installed to maintain proper regular rhythm. Okay. So here's a here's a okay here's a here's a circuit. In this circuit, so here's the capacitor charging. Okay. Once the capacitor is charged, this current stops. And then once the capacitor is fully charged, that current is stopped. And then you close this switch, and that capacitor discharges through your heart. It loses all its charge, and then it's charged again. And then you close the switch again. Okay. So. Okay. So charge stored in the capacitor, and the capacitor is discharged, and there is a current to the heart to get it started. Again, charges, discharge. Current is gone through your heart to get it started, to get the heartbeat started. Okay. So this relies on the fact that part of your circuit is still good in the heart. Okay. All it was having was starting trouble, getting the heartbeat started. Okay. If everything is fried, then you have no shot. All right, here's an interesting device, interesting system. Okay. So all this happens underwater. Underwater, seawater is a good conductor, and here's an eel. So here's the problem. Here's an eel, and here's food, another fish. What the eel will do is it'll pass an 1 amp current, either stun or kill the fish, and then eat it. But look at this. This 1 amp current passed through the eel as well. The prey died. How come it didn't die? So how do you solve that problem? Do you guys understand that? So here's how it solves the problem. Okay, so here's the fish. The current of 1 amp passed through the fish, but when it comes into the eel, it breaks that current into 150 branches. And through each branch, only 1/50th of an ampere is passing. And that's not enough to kill it. Yep. All right, so that's the solution. Okay, so by the way, we'll come to your, so in all your cell bodies, there's a 70 millivolt potential difference. So the inside of your cells is 70 millivolts below the outside of your cell. Okay, the potential difference is that. Okay. Eels have these special cells where the potential difference is 150 millivolts, twice the voltage. Okay. So these are called electroplaques. So these are the batteries of the eel, and there is a 5,000 per row. So 5,000 times that is a 750 volts. So here's 5,000 of these cells in series that are providing 750 volts. And the internal resistance is 10 ohms. Okay. And so so eel uses, so this is a high voltage device. You'll hear high voltage, low current device. So each of these guys is providing a low current. So you have 150 rows of those, all those currents add up, and then you get a high current that you use to kill prey. Okay. So the eel uses the surrounding circuit, seawater, to complete the circuit. The amount of seawater resistance is 800 ohms, through which a current of 1 amp can be passed. Okay, so Each row is a high voltage device but low current device. So you use currents from all of those, and now you got a 1 amp current which you can pass through the eel, through the prey. Okay. The current of 1 amp passing through a fish swimming nearby can kill it. Current in each of the electroplaques itself, current in each branch itself is 1/50th of that, which is 6 milliamps. So it doesn't kill the eel. Okay. Okay, so here's another device. You guys might have seen these three-way lamps, which will have two filaments. When you close this switch, it acts like a 75-watt bulb. And then you open this switch and close this switch, and it'll act like a 100-watt bulb. And then when you close both the switch, it acts like a 175-watt bulb. Okay. Okay. You guys have all seen three-prong devices, and what the three prongs do is it's a safety feature. So you see, if you have an electrical instrument device like this, and if for some reason, well, so if let's say the wire breaks and is touching the casing, okay, and then you're holding onto the casing, and the current will pass through you to the ground, and that's not good for your health. Okay, so to prevent the current passing through you to the ground, if you connect the casing to the ground, current uses the path of least resistance. It'll go to the ground rather than through you to the ground. Okay, so that's what the third prong is. That wire is connected, so the casing is connected to the ground. Okay. Of course, if your hands are wet, you're decreasing the resistance through that path. Okay. So, household wiring. So here's the power line, and like I said, every device is connected in parallel. So if this device goes bad, that device can function as well. And this way, everybody is seeing 120 volts. Okay. Houses are connected like that as well. Here's this house, that house, and for some reason, if this house, something bad happens to this house, that house can still get power, and so on. Okay. And what does the fuse do? Okay, so if this device is on, this device is on, the current is the sum of all the currents being drawn. And if you draw too much current, you might fry these wires, so you have fuses to prevent that happening. So all these devices are working on 120 volts, but there are some devices that need more power than power is voltage times current. But if you need more power and 120 volts is not enough, what you can do is provide 240 volts, and then you're doubling the power provided to the device. And the way you do that is, so one is a live wire and one is the ground. Okay, so you provide two live wires 180 degrees apart. So the utility provides two live wires, one at 120 volts and another at minus 120 volts out of 180 degrees out of phase. So it'll provide two live wires, okay, like this, and they're 180 degrees out of phase. Okay. So it's a sine wave. This is 120 volts. Okay, so this is 120 minus 120. The difference is 240. Okay, so two live wires. at 120 degrees, 180 degrees apart, and you get 240 volts, which is what you feed to your heater in the garage, to your washing machines, and so on. All right, we got 5 more minutes. Do you guys want to see how your nerves work? Okay. Neurons are specialized cells, and they form a complex network. Your brain has 90 billion neurons. Okay. And it's the most complex interconnected network. Okay. And each neuron can connect, have up to 10,000 connections to neighboring neurons and so on. Okay. So here are sensory neurons that brings input signals. Okay. And then interneurons, okay, so this is, or if this goes to your brain, then processing happens and then the output is sent through motor neurons. Okay. Okay. So interneurons transmit information from one neuron to another neuron. Okay. A signal, so here's a neuron, there's the axon. Okay. The myelin sheath, glial cells form myelin sheath. Those are sort of insulated. Those are energy-saving devices. Okay. You'll see that signals can jump from here to there, and so that's an energy-saving device. So if you don't have this myelin sheath, then you're using more energy than needed. Okay, you're inefficient. All right, so we'll see how electrical signal is transmitted down the axon. Okay. So here's the axon. And so inside the axon, so there's a minus 70 millivolts. So when the axon is it's at rest, the voltage inside is minus 70 millivolts. Okay, so it would be minus 70 millivolts. Here's a nerve impulse. What is this? Here is the nerve impulse. So at this location, instead of minus 70 millivolts being the voltage inside the axon, the voltage is plus 20 millivolts. So here's a voltage spike. So inside there, that's plus 20 millivolts. We'll come to how that happened. And when a nerve impulse travels, that impulse travels like that, down the axon. That plus 20 millivolts inside the axon is traveling like that. That's a nerve impulse. And that nerve impulse can travel about 100 meters per second. 100 meters is from here to the student center. Okay. So now let's see how that nerve impulse is generated. Okay. By the way, so if you pinch yourself, that signal is traveling at 100 meters per second. If you pinch yourself harder, how do you tell the difference? So let's say you eat hot, and then you eat Thai hot. How do you tell the difference?
There's like more actual
What's that?
There's like more actual
So the strength of this signal doesn't change. The signal is the same. So what happens is the rate at which you send signals tells you the intensity of the, okay, so that's how you tell the intensity of the heat or whatever. Okay, so if you pinch yourself harder, you're sending more signals. Nerve signals travel at about 100 meters per second. Strength of the signal is conveyed by the number of pulses transmitted. Okay, so now let's see how this signal is generated. Okay, so we want to generate plus 20 millivolts inside at this location. Okay. You can read all of that stuff. So here's the axon. Here's the cell wall of the axon. Okay, so here's the axon. And normally it's minus 70 millivolts. And what you want to do is, so you want to generate 20 millivolts there. Okay, so axon environment. The aqueous environment of the body is much like seawater. So outside the axon, what you have is sodium and chlorine ions, like seawater outside. Okay. And inside you have potassium and large negative ions. The cell wall is permeable to these guys. It'll freely let, under normal circumstances, it'll freely let these guys. It doesn't let these guys. So what happens is under resting condition, potassium ions will, because concentration is higher, they'll go out, and that's how come you have minus 70 millivolts. Okay. So once the voltage reaches to that, that prevents further diffusion of potassium ions. Now, when you're generating a nerve impulse, what you're doing is you're changing the property of the cell wall there. You're changing the property of cell wall there, and now you're making it permeable to sodium ions. Okay, so this was negative, so what will happen? It'll attract these positive ions. So for 2 milliseconds, positive ions flow in here, and this becomes plus 20 millivolts. So now the voltage here went from minus 70 millivolts to plus 20 millivolts. That's the nerve impulse. And once this becomes positive, now more positive ions can flow out. Okay? So more positive ions can flow out, and then in 20 milliseconds, the voltage goes back to minus 70 millivolts. All right, so again, in the resting condition, okay, so this was minus 70 millivolts. You change the potential of that, sodium ions moved in, and once sodium ions moved in, this becomes positive 20 millivolts, and because it became positive, more potassium ions can go out. Okay, so here you created a nerve impulse like this. When you created a nerve impulse like this, what happened? There was a bunch of extra potassium ions there, and there was a bunch of extra sodium ions here compared to normal condition. You'll have to reset that. So you'll have to move these sodium ions back and potassium ions back in later down the road. So you need ion pumps, and 20% of all your energy is spent for that. But that's down the road. We'll worry about resetting later. And that impulse travels at 100 miles an hour. Okay, that's your nerve impulse. Okay, so appropriate stimuli change membrane properties locally such that if it becomes permeable to sodium ions, leading to an inflow of sodium lasting 2 milliseconds, so near 2 milliseconds, an inflow of sodium makes the potential there inside the axon plus 20 millivolts. This produces a 30 millivolt peak in the action potential. Immediately afterwards, an increase in potassium ion flow out of the cell restores the resting potential. In an axon, charges are moving perpendicular to the charges are flowing this way, and the potential spike is moving that way. Okay, so unlike in a wire, okay, in an axon, charges move perpendicular to nerve signal movement. This is unlike signal transmission in metal wires. Okay. All right, so again, so here's an axon. When sodium ions move in, you create this spike, and once you've created this spike, that facilitates more motion of potassium ions that way, and that restores the action potential. And there is this nerve impulse which travels down the axon. And the speed at which it travels is 100 meters per second. Why that 100 meters per second? Why that 100 meters per second? So here is a meter-long arm. You touch a hot plate. How fast do you want to react? A tenth of a second. Okay, so you don't burn yourself. Yeah. All right, guys.